Right. So in today's class, we will mainly be hearing about scattering amplitudes and Gaussian domains. Before we do that, I just want to complete the discussion for us. It's about the moduli of frequencies. So just to remind you what we were talking about, you know. We were regarding a complex manifold as a bunch of patches, on each of which we have a coordinate system where the metric takes the form dz, dz. Okay? On overlaps of these patches, we have one coordinate being a function of the other. We want to match this up with some situation where these we're dealing with metrics modulo conformal transformations, and since analytic coordinate changes give us conformal transformations, the kind of functions that we are interested in are just analytic functions. Okay, so z is a function. Z on patch m is a function only of z on patch n. Z bar on patch n is a function of z bar on patch n. Okay, so we're in that situation, and we're trying to write down the factor that we get, the measure factor for moduli that we get in this language. Okay, we had it in the other language, that is, in terms of how the metric changes if you keep your coordinate patches fixed, and we're trying to transform it into this language of frequencies. Okay, so let's do that. So we had a few formulas on the board last time, which I reminded you of. The first was that the measure factor written in the language that we had before was integral b z z mu z bar z plus bz bar mu z z. And we have this definition of mu z z bar. So we have the definition of mu in general, which was mu alpha beta is equal to g beta theta del k. All of this should have a k index. Okay, this mu should have a k index for the kth moduli. But I'm suppressing that. There's no okay, so del k, so that's del like del tk, having to respect the k modulus of g theta alpha. Okay, and then we applied. Here we worked in the special case where we were starting about the metric that we worked about was flat. There were changes as we changed the pattern. That allowed us to simply raise and lower things. So reason. Okay. Now, what we were going to do was to try to rewrite this in terms of changes in transition functions between patches. Okay. So suppose we are on the mth patch. We're on the mth patch, and we've got some function z. Okay. Now, as we go from t equals 0 to t equals 0 plus delta k, our coordinate changes from z to z plus v. Okay. So the new coordinate z prime is equal to z, okay, plus delta tk, but that's press the k index, times v. Okay, let's call this vz. We also have the z bar, z prime r, z bar, plus delta t times vz. Okay, and this coordinate change has to be chosen so that up to a conformal transformation. So that up to a conformal transformation, the change in the metric is this change. Is the change generated by this derivative. That's the condition we want. Okay? So now in the new coordinate, our metric is dz prime, dz prime. Okay? So now what we have to do is to take this metric in the new coordinate and rewrite it in the old coordinates and equate that metric with the slightly modified old metric up to conformal transformations. So what do we get here? You see, what is dz prime to start with? Dz prime is equal to dz plus delta t into del vz by del z delta z plus del vz bar by del, sorry, dz by del z bar delta d. dz, dz bar. Okay? And similarly, dz prime bar is equal to dz bar plus delta t into an analysis formula. Right? Del dz bar by del z dz plus del dz by del z bar. Now we're working the first order of delta t. So let's find with the new metric. So the new metric, so dz prime dz bar prime, to first order in delta t, has two kinds of terms. There's a term that's dz dz bar, and that has 1 plus some stuff. Now some stuff is this del dz by del z plus del dz bar by del z bar goes into delta t. Okay? Plus we have a term that is dz dz we have a term that is dz dz, and that comes from this with this. That comes from this with this. So we have del vz bar by del z, and plus we have a term that's dz bar delta t plus del dz by del z bar delta t. Right? So let's count. There are a total of 4 terms according to delta t. 2, 3, 4. As there should be. This with these two and this with this. So we got. Okay, good. Now, the first question is what about the first term? Now, about the first term, that's very simple. You see, that term here can be absorbed. Well, that term is a conformal factor. Just because it takes the metric equals dz dz bar and is dz dz bar times something. We are only interested in changing the metric modulo conformal functions. So this term doesn't work. This is simply the statement that if we have a coordinate patch and we perform a change of variables on that coordinate patch, that is analytic. Well, that doesn't change the complex. Okay? So this part we're going to throw away. This part we have to equate with the change. Okay. So this part here is to be identified with delta gzz. Del dz bar by del z. But delta gzz by the definition of this was equal to mu z z bar. Right, because this is delta gz z, and then we get a z bar that will be this. By This is, yeah. So delta d z is this times delta t. And this times delta. Okay? So we've identified then mu z bar is equal to del v z bar by del z. And of course, symmetrically, mu z bar z is equal to del v z by del z. Is this clear? Okay? So let's proceed. So what we are interested in doing is evaluating this object. So all we have to do is replace this mu z bar and mu z bar z with these things. Okay? So the insertion factor, let me deal just with the holomorphic part, the anti-holomorphic part. As usual, very similar. It's 1 by 2 pi, I'll ignore 1 by 2 pi. Bzz into del z into del z. Z bar of bz. Yeah. Okay? Now, we've got this d2z. But we've got this dz bar. Okay? So, we do the z bar integral. What's left behind is a z contour integral surrounding the region of interest. Okay? So, this is equal to integral over a contour surrounding the region of interest. Okay? Integral over a contour surrounding the region of interest, bzz dz. Is this clear? Okay, maybe factors when you do it properly 2 pi r and do that. Factors. Okay, excellent. So now we have this expression here, but we set it up, in the region of interest. Now we have to be a little more clear about what that is. So let's suppose we've got 3 coordinate patches. Let's call this M, N, and Q. We were supposed to do this integral over the whole manifold. Okay? Because never counting to 2 points of the manifold twice. Okay? So we can choose to do we can choose the boundary of the nth manifold to be, say, what's happening here will depend on how this patches meets other patches. Okay, so let's leave that unsaid. We can choose the boundary of this guy to be here. So that gives you that the boundary of the qth manifold is here, and the boundary of the nth manifold is here. So the nth manifold has this boundary, the qth manifold has this boundary, and the mth manifold is this. We can choose to regard these integrals as partly being the mth manifold, partly in the pth manifold, partly in the qth manifold, segregated by some boundary we choose. Is this clear? So, let's look at what we're going to get. Let's look at what we're going to get on this point. On this line, the line that lies between them. From M we have to do the integral which gave us this line integral that we missed. But we also have to do a similar line integral from N. We'll also have to do a similar integral from N. Okay? So what does that seem to be? Well, little more careful in our notation. So far we've been dealing with just one patch. So we've been allowed to be blasé. But, on different patches we can do different coordinate changes. And the coordinate changes are written with respect to different vector fields. So I'm going to put two indices here. The first one is M, which tells you that this is a coordinate change happening in the mth patch. And the second one I'm putting here is M, which tells you that once I've done this coordinate change, I've got a vector field. Now, if I've got a vector field, I can view it in any coordinate system I want. Mz is the vector field of the mth coordinate change viewed in the coordinate z. Is this clear? That the vector field is this times del by del zn. Is this clear? Now, what are we going to get from the other side? What are we going to get from the other side? Well, let's see. You see, okay, before I work that out, let me first work out let me work out the following question. What is the change in the transition function on this line? Okay, so what is the transition function? The transition function is what Zm is as a function of is Zm of Zn at some particular value. The transition function is the analytic change of coordinates between the mth and nth patch. And this thing is a function of t, but the transition function is viewed at a particular value of t. So the change in the transition function is del Zm by del Zn at constant t. Is this clear? But let's see what that is. You see, when I change t, sorry. So Zm is this function, and so what I want is how much this function changes. How much I want to evaluate what delta Zn is by delta t at fixed Zn. So this is the thing that I want to do to evaluate what the change in the transition function is. It's how much this function changes at a fixed value of the coordinate Zn as t changes. Now, how do I evaluate that? Well, that's very simple. Because I know how these functions change. So the function Zm has changed how? It's changed like this. Well, okay, maybe I should just give you the formula and then explain. So this is equal to Vm minus del Zm by del Zn at constant times Vn. This is my thing. Okay? Now let's understand this one. This formula, how does this formula go? You see, if I change t a bit and I fix to a particular point on that, okay, then Zm changes. How much does it change? It changes by, its change is Vmm times delta t. That is the change in Zn. But Zm is not the only thing that changes. Zn also changes. Okay? How much does each change? So delta Zn is equal to this. Delta Zn is equal to Vnn by delta T obviously. Same formula, just put it in touch.
Zm also has a 7
Zm. Yes. So what I'm asking is, I'm fixing a point in the manifold. I'm asking, how does the value of Zn change?
Right. So it depends on two things, the T and Zn, because you're looking at the line.
No, I'm fixing a point on the manifold. Okay? So I stick at the same point and I ask, at that point, as I change T, how much does Zm change? That is completely intrinsic. That's intrinsic to the mth batch. Has nothing to do with Zn. Okay? Similarly, I fix at the same point on the manifold and ask, how much does Zn change as I change T? That's also completely intrinsic. It's got only to do the nth batch, nothing to do with the mth batch, and it's given by this formula. Now what I want to know is, how much does this function change? Okay? It's a line, you don't understand.
No, I mean, it's that thing that you're doing, the m and
this function is this function.
pictorially, can I think of this as...
This function will be evaluated on the line. Okay? Now, how much does the function change? Well, firstly, Zn changes because the value changes. So clearly there's a part of the change of Zn, which is just Vmm times delta T. But, you see, the argument of the function has changed. This is now to be equated with delta, the function Zm, not evaluated at Zn, but evaluated at Zn plus Vnn delta T. T plus delta. Let's suppress this. I'm suppressing the T effects. Everything is now delta T plus delta. Is this clear? So, the change in Zn is this much, but that is the change in the function, not at Zn, but at Zn plus Vn delta T. Because the argument inside the function has also changed. So, the change in the function at Zn, the delta Zn at Zn is equal to delta T into Vmm minus what you get by Taylor expanding, you take the left side. Okay? Minus del Zm by del Zn, a constant T, times Vnn. Okay? So this quantity gives you this object. Del Zm by del T. Okay, so this object is equal to that. That's the formula. Is this clear? Okay. But now look at this. This quantity here multiplies a vector field by a transition function. And therefore just gives you the vector field in a new set of coordinates. Okay? So this quantity is equal to, this quantity is equal to Vm in the mth coordinate minus Vn in the mth coordinate. But this is exactly what we get by doing this integral. You see, you saw that by doing the integral over the mth patch, we got Vn in the mth coordinate. Integrated over dz. Here, if you did it over the nth patch, you get Vn in the nth coordinate integrated over dzn, which is the same thing as Vn in the mth coordinate integrated over dzm. Okay? This is just a coordinate change in that result. So that's basically you want to evaluate everything in the same coordinate. So vector field, in the end you evaluate in the same coordinate. And because one of these goes clockwise, the other goes counterclockwise, there's a minus to it. So if you do this thing on this patch, on this line, the path that you get from this patch and the path that you get from this patch combined together to give you exactly this object, which is the change in the transition function along the line. Precisely it says dZn by del Zn by del t constants. Okay? So we see that the full answer here, I mean the holomorphic path is 1 by 2 pi equals bzz del z m by del t at constant zn. Changes the transition function. This is over the mnth patch along this line. Then this will take over with del zm by del t at constant zq. And so on. The whole thing will be closed, will be some closed layers when you look at the coordinate. Okay? So this is the answer. This is the answer for what the insertion in the path integral has to be when viewed as a function of the transition functions, in terms of the transition functions. Okay?
It does not depend on the choice of these lines
Well, the topology is fixed by how the patches act. And how you choose this, precisely does not depend just by holomorphs. This is holomorphic. More contours. You think about this meeting point. No, you see, the original thing was completely independent of how you chose to slice things up.
That is my so that so this
Yeah. Yeah. Yeah, okay. There may be something to check directly, but it has to work. See, one thing that's clear is that if you take this shape, this thing and wiggle it around, it can't change because of holomorphism. You see, this is a holomorphic function. You move it around, you get the same answer. You may have to think more about moving this point. No. Okay. So, now let's try to work out. Now let's try to work this whole thing out in a very simple case. This simple case is going to allow us to put all the moduli of our scattering amplitude on the integral. So if you remember what we had that our Riemann surface had some moduli. And then, if you remember long ago when we actually looked at the path integral, tried to fix all the additional degrees of freedom and so on, and we found that we had to integrate the vertex operators. Some of the integrals of the vertex operators we use the unfixed diffeomorphisms to fix. The other ones we still had to integrate the positions. Now, unifying way of thinking of this is to think of the manifold over which we are doing our integrals is the space of Riemann surfaces with a set number of punctures. And associated with each puncture, there is a new modulus, which is basically the position. Okay? So, instead of, that's the way we're going to view the scattering. We're going to view the scattering amplitude as an amplitude that has an integral over this. Hello? Yeah, hi, Imran. Imran, I'm teaching a class at the moment. Can I call you back in? Yeah, okay. Okay, so, great. We've got these, we're going to think of this as modularized space of Riemann surfaces with as many punctures as there were vertex operator insertions, and integrate over the whole modularized space of that Riemann surface. Now, how do we associate this modulus with the position of the function? You see, the position of the function, as we said, is just where in a particular patch that puncture happens to be. So, say we've got the end of the patch, and we've got a puncture. That puncture can be anywhere. Okay? So, what we can do is just surround this puncture by its own patch. Okay? And make the coordinates, say this is Zn. I'll describe some new coordinate system, let's say Z alpha. Okay? So that Z alpha is simply equal to Zn plus some shift, Z. How much you shifted tells you where exactly the insertions. So let's say this again. In our new coordinate system, the Z alpha coordinate system, our insertions always are large. The fact that it can be wherever it wants on this patch is encoded in this coordinate. Okay? Good. So for this simple case, this coordinate system is entirely in the bigger, this coordinate patch is entirely within the bigger coordinate patch. Right? So this shape is very simple. The spin line is just this. Okay? Also, del Zm delta T Z, no? It's a parameter of how much you shift, how much the modulus has changed. And del Zm by delta P is just a constant. Because it's the linear shift. Okay? Okay? So let me call this T. T is the position of the insertion.
Which is different from the parameter T.
No, it's the same because it's a modulus. Its modulus is associated with this particular puncture insertion. That's why I'm calling it. It's not a modulus of the Riemann surface, it's a modulus of the puncture. But it's one of the moduli of the puncture Riemann surface. Okay? So what I was supposed to do is evaluate del Zn by del T, evaluate del Zn by del T. In this case it's Z alpha by del T. I get a constant. Okay? And so the insertion is integral dz with nothing. And this integral goes over this contour. Goes over a contour that surrounds the insertion. Over a contour C that has the insertion. The insertion has some operator, so the insertion operator. Now let's see how this compares to the old rules for scattering amplitude. Clearly, because this is one of the moduli of the problem, this is one of the integrated vertex operators. Okay? It's one of the integrated vertex operators, and therefore, according to our old rules, we shouldn't have had a C insertion in that operator. It should have just been the superconformal, the conformal primary. The matter conformal primary. But now, we have to recover that old rule with this So what should this op be? It's easy to see what it should be. If op is equal to O times C, let's call it C times. Suppose op was equal to C times O, where O was the conformal primary, the matter conformal primary. Then what would we get here? We get dz. And then we pick out the pole of the B of OP. But O is purely in the matter sector, so there are no singularities between B and O. So the only thing that we really get to see is we get up to some signs. We get O by Z plus holomorphic, and so we will get O. So we will have integral over dt, that's position of insertion, and O. Reproducing our old rule. Old rule says that you should insert just the conformal primary and integrate it over the worldsheet without the C insertion. So this is very nice. This tells us that if we think of insertions in this way, okay, insertions is associated with moduli of the puncture in one surface, then the operator that we have to insert is C times O. That is always, the rule is that for all operators, you insert the operator, for all scattering amplitudes, for all insertions, you insert the operator that is dual to the given state of the conformal state. Okay? But you have to integrate over the moduli of all, the full moduli space of the theory. So some of these operators, those that correspond to the moduli, are surrounded by the appropriate modulus weighting factor. That appropriate modulus weighting factor in this case is the integral B, which kills us. Therefore recovering the old rule. Okay? So our new rule goes as follows.
Either write down the integrated version of the operator, or write down C times the operator with the B insertion also.
With the appropriate B insertion for the modulus. So we think all moduli now are equal to it. The modulus of the Riemann surface as well as the moduli associated with the functions. So this in some sense is the nicest and most geometrical formula for scattering. Okay? It involves an integral over a moduli space, which is the moduli space associated with n punctured Riemann surface. For every modulus in this integral, there is an associated B factor. In some way of parametrizing this moduli space, you can get rid of some of these moduli things rather easily at the expense of killing these C's. But abstractly, it's just this integral over this n punctured Riemann surface with B insertions that we have understood.
Could you remind me what the C to the O is?
Sorry. C is the ghost field of the line string. O is the conformal primary that corresponds to the state that you get.
Okay.
So the operator that you have to insert here is C times the conformal primary.
Okay.
So that when we do the integral over B, that kills the C and gives you just a conformal. Okay. Now, we should have had all of this discussion like a year ago. We didn't because at that point we just had some abstract concepts. Some way of making some well-defined formula look more pleasing to some eyes. But now it was useful to have this discussion. This is often the way things go with abstract stuff. You know, people with a certain inclination, and that includes me, tend to think, oh, this is just some fancy way of saying something I know, so I'm not interested. However, that fancy way is often useful for generalizations. The thing that you know in a particular way, you say it in some slightly fancy way that allows you to generalize it to situations where you don't. That's often the use of fancy ways. Okay, so this is one use in this situation. This fancy way of wording the bosonic string scattering amplitude has a natural generalization to the solution. Okay? And this natural generalization, I will only talk about next class because otherwise Jyotirmoy won't have time for this. for this exposition of scattering amplitudes. But I'll just give you an advertisement. The natural generalization will include, always putting all operators in the natural conformity theory. Okay? And introducing some factors for corresponding to the integrals over superconformal moduli. We will see what they mean. And just like this fancy way reduced to giving us integrated vertex operators by dropping the C, that fancy way will reduce to our old rule of inserting appropriate picture changing operators once we work it out correctly, giving you a reasonable justification of this whole rather ad hoc picture changing rule. Also, apparently allowing, giving you a principle to resolve sort of subtle ambiguities that arise at happening. Okay, any questions or comments about this stuff? Next lecture, we'll go through that the superconformal version of this. And
this insertion can be copied as something which is in
this insertion
the bosons.
Well, you may want to think of like the B contour in some sense, like that.
In the sense that you remove C.
You remove C.
Yeah.
In some sense,
for example, can we just write this in terms of the JPIs?
Oh, that I've never seen that. I haven't tried to do it, but I've never seen that. I suspect that there was some immediate way of doing that. No, I don't. My guess is no. My guess is no. That whole JPRST business depended on the fact that in the beta gamma, if you try to rewrite the beta gamma path integral in terms of phi and zeta eta, there's a leftover insertion of zeta that you must introduce. And that was very important to this whole picture change. I don't know any analog of that statement. So I suspect there's no clean analog. So at this level, there will be a clean analog of the superstructure. Namely, there will be a clean analog of this formula involving integration over all moduli. But I don't know of any analog of the picture change. Other questions or comments? Okay, so our plan is, next lecture I'll go through the superconformal version of this. I'll ask also for a volunteer for the subsequent lecture to tell us about the one-loop amplitude which we discussed. This is the one-loop amplitude that verifies that anomalies do cancel in the string theory. Appropriate FB term. Okay? And then we will declare that we have completed our study of Wilson's up to chapter 12. Okay? So we've completed the formal part of the study of string perturbation amplitudes. Then we move on to the more immediately physical things about in chapter 13 and chapter 14. And then we'll have some discussion of space-time physics and the discussion of the work. Okay, so we got through our introduction. The string theory course, a rigorous string theory. By rigorous, I mean rigorous in my sense. That's something that goes through every idea, touches on every idea in some way. Has a part that talks about perturbative string theory. Okay, just how do you set up perturbation theory? How do you? Apart from one important omission, that is the sigma model business. How do you generalize the string theory moving about in flat space? We will soon declare victory. We will soon declare that we have completed our study of that stuff. Of course, unfortunately, that study is just a prelude for doing anything interesting. We don't really care how to computer amplitudes most of the time. But we need to know the rules in order to do anything interesting. Okay? So, what we will have done in this, after declaring victory, is completed the background so that when we start doing anything really interesting, like ADS, EFP, really interesting stuff, I don't have to say it can be shown that. What we can say is, as we have seen that. So you have necessary background for doing the interesting things in the string theory. Leads to. So it's sort of a strange situation where you go through a year or year and a half of coursework just to set the tone for doing anything interesting. And this is interesting for mathematical physics at the moment, not yet for physics or experiment. But still, that's the state of the subject. And now you've suffered through the technicalities. We come in to more immediately interesting things very soon. So it's payoff time, of course. Okay, now get your mind. Oh, there's Berkowitz also, so that would be payoff time. Some compromise.
Okay, I'll start off by some of this very from the maths class. At first, I'll be completing certain 3-point functions. So in the last class, we computed the 3-point function of three K bosons in the type 1 theory.
And we didn't quite complete that one bit.
So there was this churn pattern factors which was left over. I just complete that discussion. So the correlation function that we are calculating is this, but this is a picture. And these are the vertex operators, and since these are all boson, I consider 2 vertex operators in the -1 picture and 1 vertex operator in the 0 picture. And so for the disk 3 insertions, I also need to consider the 1 equals to 2 here for completeness, and I have the corresponding matrices here in the vertex operator. So let me write down the vertex operator. So in the -1 picture, the vertex operator is modular factors of G0, which I am using for this discussion. And the vertex operator in 0 picture is the resultant phi, and this is replaced by star I times x star plus alpha. Now, if we calculated what the correlation function would be without considering these PAs. Now, if you consider these PAs, then this circle would be considering trace over TA, TB, TC, and this and the other diagram 1 to 2 would also contribute another trace over TB, TA, and TC, and when I exchange these two vertex operators to get the same object, then I'll get a sign because of this. So that is minus, and this will give me trace TA, T, commutator, and CC. So the result that we obtained in the last class, we need to multiply that by this factor to get the answer. This is also consistent with the field theory expectation.
What's the answer for the abelian case?
For the abelian case, this commutator vanishes.
And so we get 0.
0.
Why is that the right answer?
Oh, there's no interaction between gauge boson and slide. Now, we'll look into, let's say, 2 fermionic operators interacting with a gauge boson in type 1 of OS. So that would again be similar to this calculation, how the vertex operator would be different. But now the fermionic operators is in picture minus half, and the phi current conservation tells me that I have to consider the total phi charge should be minus 2. Therefore, since I am considering 3 point functions, I would consider the 2 fermions to be in the picture minus half, and the one boson, the gauge boson, to be in the picture minus 1. So this is something that I need to calculate. Next one, 2, and this is the gauge boson, minus 1 picture. Now let me write down these fermionic, this boson, gauge boson vertex operator we have already seen in the minus 1 picture. It's just e to the power minus 5 times sin u, e to the power ikx u, and the fermionic vertex operator would be e to the power minus 5 by 2 times theta alpha u alpha, where this theta alpha is the string field that was introduced earlier. This was defined in the following way: exponential I times sum over SA HA, where HA are the bosonized version of the styles. However,
And SA is
are the corresponding values under the 5 card terms of SO.
what values can they take?
They can take plus minus half values. And so
Each SA is like a plus or minus half,
Right.
and the sum of product of signs is positive, let's say.
yes. However, in this definition, Lorentz invariance is explicitly broken because we have to pair up the fields. But in this way of describing things, we find it convenient to keep Lorentz invariance. Therefore, we would consider this theta as to have a Lorentz index alpha, the fermionic Lorentz index. And it would be, I mean, it's not straightforward, but one can, obtain what exact S vector it corresponds to in this way of writing this. Okay.
It's quite straightforward. Because
Yes, I mean, you just look at what alpha means, which string vector, and then you plug in the values here to obtain that.
Yeah. Ideal values under the various terms is manifest.
Right. Right. Yeah. So, however, here we'll be exploiting the loyalty invariant, so we keep the alpha in X. So, so now we split this. Oh, sure. Now we split this correlation function up into different CFTs. The CCFT is obvious. It's the same thing that we did in the last class. This will give us a x12, x23, x31, consistent with control invariants. And then we have to worry about the phi's. So we have to calculate something like e to the power minus phi by 2, e to the power minus phi by 2, e to the power minus phi. Okay. In order to compute this, we recall some formula, which is like e to the power product of e to the power I, k, x. I mean, some formula, some analogous formula in the case of Bosonic string, which we had used earlier. But there is some A's, let's say. This goes as some factors, x to the power ij, take xij, k to the power, again with suitable choice of alpha, I dot k, product, I less than. Okay, if we do that, then we'll find, so we have to incorporate the associate i's, and on doing that we find this goes as x to the power 1, x to the power 1/4, half.
What are the x's?
This is, so I'm labeling this as 1, 2, 3. X's are the two guys, these two, x1, 2, and x1, 3, and 2.
Excellent. Now could you just argue out the 1/4 and the half power?
Yes. So this is okay. So here we have to identify k as I times half. In fact, minus I times half.
Because in the bottom formula you're using alpha prime equals to
Alpha prime equals to half.
half. Oh yeah, we know.
Yeah. So now, so here I use k equal to minus I times minus I times half. So k1 equals to minus half. K2 equals to half times I. So K1 dot K2 is going to give me minus of 1/4, which is this.
Right.
And K3 is I, just I. So with K3 with this is going to give me a half with a minus sign. So it's a.
And just a way to remember, without remembering the formula, to remember a master formula, it's e to the power a times x times e to the power b times x, and if you have many of such things, it's just a sum over e to the power ab times the 2-point function. This is always true. The product, it's a formula that follows from Gaussian integration. Now the 2-point function is minus log.
Right.
Okay? So the half to the half will give you 1/4 times minus log, so x to the power 1 over x to the 1/4. But the half to the 1 will give you 1 over x. Perfect.
Now, the next thing that we are going to do is we have to look at. Let's look at the. Okay, so we have to evaluate something like theta alpha, theta beta. Yes, 1, 2, sine 4 different things. And you have the two theta from these two vertex operators, and you have a psi from it. So in order to do that, let's first write down the correlator between two thetas. So this we'll do by arguing about conformal invariance and Lorentz invariance. Now this would be proportional to C alpha beta, where C is the charge conjugation matrix. And so in order to figure out the dependence on Z, let's find out the weight of theta. Okay. So the weight of theta can be found out from this expression. This being a vertex operator has weight 1, and e to the power minus phi by 2 has weight minus half into minus half whole square minus plus half, which is equal to 3 by 8. 3 by 8. And therefore the weight of theta is 1 minus 3 by 8, which is equal to 5 by 8. Since we have two thetas here, so it's 5 by 4, and therefore the dependence is x to the power 5 by 4.
Good. Could you also argue that directly from the formula theta in terms of H space?
Okay. So we can of course argue for the x dependence, but this is very easy. So theta in terms of the h is e to the power I. So I some number times h into e to the power I times some number times h, and so this should go as, actually this number is important. So
the number is always plus minus half.
okay.
So the weight it won't matter if it's plus or minus half. What is the formula for the weight of e to the power I kh?
So it's x12 to the power k dot.
No, k1. Just the dimension. What is the power? Oh, I see. You're calculating 2 by function. I see.
Yeah.
I see. But what is that? Just what is the scaling dimension of e to the power I? I times k.
So it goes as k squared.
It's k squared by 2.
Yeah, k squared by 2.
Okay. Now can you evaluate the weight of theta? The scaling dimension of theta directly.
Oh yes, yeah, fine. So this is k squared is k is plus minus half. So this is 1 by 8.
And how many h's?
And there are 5 h's, so that's 5 by 8. This is the same.
Thanks.
Okay. So this is the second relation, and also I would like to write down the relation, the OPE of theta with the psi.
Jyotirma, I suggest now you clear what you don't need. Or you need it.
I need these relations, and I'm evaluating this. So let me clear.
You can clear what you're evaluating. Everyone. You need the relations, leave that. Just clear the left hand side.
So I want to evaluate this, and I have this expression. Let's look at the OPE of theta and psi.
Jyotirma, why don't you also rub a 3-point amplitude type on this? Get more space. Let's start with the top.
Okay. So this OP, we again argue through conformal invariance and the weights that this should be proportional to theta of theta alpha beta mu and divided by x to the power half. Okay, plus 7.
There is no, sorry.
No, there's no C here. The C comes from this. Now, the 3-point function that we were interested in.
Wait, give us the argument.
So, okay. Firstly, the dependence on x is fixed by the weights.
So how do you know that's a theta? Okay.
So this is in the, let's say, in one of the parallel vectors, and this is a vector, and we are taking a product of them. So it should have something like an anti-parallel vector here. I mean, anti-parallel spinor here, and so that fixes this dependence, and then the weights are determined by.
Just in Bozanai's language, suppose I was looking at a particular term. Okay, so I was looking at theta with all pluses and psi with the minus. So suppose the theta had all pluses.
Okay.
So write that down, e to the power I by 2 psi over h. Yes. And psi was e to the power minus h. Minus h1. That particular side. Now, what would we get from doing this?
So it will click only when this is h1, and that would be like x to the power.
Firstly, yeah.
Okay, basically what I should do is maybe I should expand it out and use the log.
Yeah, just there are the 4 of the h's go along for the right.
Right. So it's just e to the power sum over a equal to 2 to 4 h.
H times something here. This is the involves h1. So what? Now right off the path it's just h1. Fine. 2 to 5.
2 to 5, right? So this is the OP between e to the power I. So this is the OP between e to the power half h1 I times h1 e to the power minus h1
Minus I.
Yeah.
The side was right at the top. The minus I.
Then it's just x to the power minus half, right? Because it's
X to the minus half times what?
x to the power minus half times 4.
Firstly, what is x to the minus half, and secondly, what is the name?
X to the power minus half because of the thing that I wrote down. It's x to the power k dot k1 dot k2. Here k is half, and here k is minus 1. And the rest of the thing is e to the power normal order, e to the power I half of h1
With what sign? Minus I. Half. E to the power minus I by 2. Oh, you were writing that. You were going on. Sorry.
yeah, so e to the power minus ih,
Which is equal to
h1.
h1, right, which is equal to e to the power minus half.
yeah, the most keeping just the leading.
Yeah, so it becomes anywhere.
So it becomes exactly. So this is an example of formula. One square root x, and you get an anti-parallel spinner.
Right.
Yes. Okay. By the way, the thing that you get on the right hand side, then that OP is it in our GSO projection?
Oh.
It doesn't matter. It's just intermediate set.
Yeah, but this thing is predicted out. then okay, then we don't need to argue. Sorry, it's great. I got some other argument. Okay, fine. So okay, then this is so this object now theta alpha, theta beta, psi mu. I will use these two relations, this relation and this one, to write this as so it's C times gamma alpha beta. And what are the singularities? So as I take these two objects here, I should get a singularity which was like about half. So if I label them 1, 2, 3, I should get a x23 to the power half and x13 to the power half. And if I take these two together, I should get no. The rest of the thing will be determined by so that's basically the correlator. So the rest of the thing, the dependence will be determined by the conformal invariance, which is in this case, this is 5 by 4 plus half, and so this is this is 5 by 4. Oh, right. Plus half, minus half, minus half. The two minus halves come from this. So that's basically 3 by 4. So this should go well, x to the power minus 3 by 4.
X what?
It's 1.
Okay, now just check that all, have you checked that all OPs are correct? All singularities are correct?
Yeah, I haven't yet written down the OP between theta and theta.
Okay, haven't just written down.
So that is reduced from these relations. Okay. So the OP between theta and theta, therefore, okay, this I don't need immediately, but I'll need at some time later. So the there will be a root 2. Yeah, the root 2 is this. So the OP between theta and theta, let me write it down since I'm. This is going to be. In fact, let me include the total vertex operators, which I will need ultimately to write. So which is e to the power minus 5 by 2, e to the power minus 5.
But why don't you give us theta and theta first? And we can understand it.
Okay. Theta and theta would be from this relation, it will be C gamma mu alpha beta psi mu divided by here this is 5 by 8, 5 by 4, and here this is half, so 5 by 4. Half minus 5 by 4. This is
5 by 4 minus 2 by 4, which is 3 by 4.
2 by 4.
Half the same as 2 by 4.
2 by 4. Sorry. This is minus 3.
Which is what you have there.
Which is what I have there, and therefore x to the power 3 by 4.
Of course, our OP also has the identity. The thing you wrote down first, 2 by 4. Theta alpha, theta beta also has a term that is proportional to identity divided by x to the power 5 by 4. And identity meaning the
Yes,
transfer.
but Right.
Charter.
Right. But when I take expectation values, I get this expectation values.
Okay. And sorry, one more irritating question. Suppose you were to use the bosonized form, could you directly see something like this? So,
Okay. So it's like the product of two spinors giving a vector.
okay. So suppose I do
Hold on, giving a scalar. Okay. So due to the presence of this C, it is only true that it will be non-zero when this is a spinor and this is an anti-spinor. And therefore, in the product of the spinor and the anti-spinor, there will be a vector. There will be a scalar.
scalar. That's
Getting a chiral spanner into chiral spanner, getting it.
Chiral spanner.
Chiral spanner should give you odd forms.
Right. Oh, right. This 10 dimensions. So chiral spanner times chiral spanner should give me odd forms, and vector is 1.
Let's take an example. Let's take all pluses and 4 minuses and 1 plus. Both chiral.
Okay.
Now both merge.
So it's e to the power.
Jyotiman, clear everything on the right hand side of the word. Right hand side.
But this result is
Right hand side. Right.
And okay. Let me just write it down. Now I am trying to do e to the power sum over.
Write it out explicitly. Don't sub over. Yeah. H1 plus H2 plus H3 plus H4 plus H5. And put 4 minuses in any two slots you choose.
Now this is going to give me
Firstly, what is the numerator? Before working out the formulas, what is the operator that's left over?
operator that will be left over is the normal order of these two.
And which is what once you've
Which is basically 1, 0, 0.
right. So write it down.
Oh, okay.
So e to the power I times
I can half.
no half anymore. Half plus half. So H1. So that's one of the signs.
That's one of the sides.
Is that's the first thing you see. Okay. Now what remains?
So
Now as you say, what remains can be worked out by putting systemation.
Yeah.
Okay, and we'll get the answer. Okay, see? Right. Okay, suppose. Okay, I should complicate your life. So, but suppose I had 5 pluses and 2 minuses.
So it will be H1 plus H2.
So then you would have got a much more complicated operator on the right hand side.
Right.
You would have got something with H3 plus H4 plus H5. Wouldn't have been a sign. But so
some combination of size.
it would have been some combination of size. Why don't you have that anymore? You only have the side, the term that is proportional to side. You gave us an OP, and
No, there was a sum, right? I mean, you had C, gamma, mu, alpha, beta, psi. So there was a sum between these two.
but everything that you have is proportional to side. You never have terms proportional to products of side. Why not? Firstly, if you could have one size, or you could have what is the next number of sides you could have on the right-hand side? Can you have 2 sides?
No, I can't have two.
You can't because chiral is chiral.
This chiral is chiral, yeah.
So you could have 3 sides.
Yes.
Okay, what is the weight of 3 sides?
3 size is 3 by 2.
What is the weight of the things you're starting with?
Yeah, it's 5 by
5 by 4.
5 by 4.
What is larger, 3 by 2 or 5?
Yeah.
So there's no singularity associated. The only term that is singular is with one side. The other terms exist in the OP, but they're not singular. Okay.
So
It's an example of Loganagham's rule. You take two kite spinners and you get all odd forms. The odd form that you produce is the vector,
and
but then
odd form
there's a three form which is psi, but it's not singular. Okay, please. Oh, well, just one more thing. Where is the final form? Oh, I asked you that.
Yeah, I'll look at it.
Excellent. Now I wanted to ask you a question about this. Suppose I take 1 to infinity. Okay. I take 1 much larger than 2 or 3. Where is the dependence of this correlator x1?
Okay, so it will be twice the weight of 1.
Yeah, well, let's read it off from there.
So let's see. So here it will be 3 by 2 plus half, which is 5 by 4.
5 by 4.
3 by 4 plus half, which is 5 by 4.
And divided by this?
Divided by 2 is 5 by 8. And so basically, when I take it far away, the only thing that will contribute, if I think of bringing this and taking an OP with this composite operator, whatever, is the part of this OP where this object is the operator itself, and so that will determine the weight to be.
Yeah, it's completely right at this state, so it's clear to everyone else. You take 1 far away, you take the other group. Now, because you can expand everything else in the other group. It doesn't matter if it's 2 point, 3 point function, 4 point function, n point function. Everything else in the other group, in an OP, the only part of the OP that will contribute is the part where the OP gives you the same operator, because 2 point functions are direct. And so it's a general rule that in any such correlation function, you take any given operator after infinity, keeping everything else finite, and the dependence on the coordinate of that thing will be 1 over x to the power twice that dimension of that operator. You can see that very explicitly in this formula. If you take 1 to infinity, you got x to the power 5 by 4, which as you said was twice of 5 by 8. If you take 3 to infinity, you get 1 over x, and the dimension of psi is half. So half into 2 is 1. This will be a feature of all the OPs you will trust. All the correlations.
Okay, now let you enter the result. The result of 3 point function of 2 fermion. And
now, Jyotirmoy, why couldn't I have added anything analytic to this?
This is
Yes. Suppose I was, you've shown us that all the singularities are introduced. But if I add some analytic thing to this, it won't affect singularities. Why can't it?
Yeah, so I mean, one way would be to say maybe you were saying that this should be projected out by GSU projection, and so.
Yeah, okay. But this is just correlating functions of conformity.
Okay, so then it will be like so basically it's the argument of polymorphicity. Actually, I can.
Of you calculate. You calculate till you find this. But from on general grounds, as you said, OP is determined singularities. You've written down something very reasonable.
Okay, so one way to say it would be like I know what are these objects, and therefore I can determine the X dependence. I mean, what the X dependence is completely in this OP, because I can calculate the OP of e to the power h, e to the power h times c.
You could do it by explicit calculation. But there is a general argument that disallows analytic dependencies, additional analytic dependencies. We just said the general argument to this. Explain that. Suppose something is analytic, then how does it grow at infinity?
It blows up basically, but two-point functions will not blow up.
We had a general argument that the dependence on x1 has to be 1 over x1 to the power 5.
Right.
As x1 goes infinity.
Right.
The dependence on x2 has to be 1 over x2 to the power 5. Dependence on x3 has to be 1 over x3 to the power 1. Anything that is analytic, that is by which I mean has no further singularities, must be a polynomial. And so will grow at least as fast as it grows, which is not. Okay? So the behavior as things separate out, basically cluster becomes. In fact, there's no one point function. Essentially tells you that you can't add anything analytic. Good.
Okay, now you can see whether the X dependence cancels because we fix this coordinates and you can check that. So here I have x12 to the power 3 by 2, and with that I need to combine x12 to the power 1/4, so that gives you 1 by x12, that cancels with the C contribution from the conformal rows. And similarly with x3, so this is half plus half, that's 1 by x13 and cancels 2. And with x2.
Excellent.
Okay, so
what is the final answer?
So the final answer would be, also this, we have to worry about e to the power I kx, this OP.
But it turns out to be
just the delta function.
ignoring delta function is just 1. That's 1. Hey, we have to terminate this here. Yeah, and it turns out to be just 1 for the same reason we talked about last days.
It's right. You can also calculate explicitly, put in the values then.
No, but because k square is always
Exactly.
because all three
by
k square
calculation I meant that. I mean x to the power it will be k1 dot k2 and k1